March 19, 1940. RAF Mildenhall, Suffolk. Flight Lieutenant David Balsden watched cannon shells stitch a neat line of holes down his Wellington's starboard side. Through the torn fabric he could see stars, not through a window, through the fuselage itself. The geodetic framework beneath the shredded linen stood exposed to the freezing slipstream, a skeleton of curved metal strips crossing each other like basket weave. The aircraft flew normally. Controls responded. Engines droned steadily. Physics said this shouldn't be possible. The Wellington disagreed. Before we dive deeper into this story, if you're finding value in these forgotten chapters of history, hit that like button and subscribe to the channel. Drop a comment below telling us where you're watching from, whether it's London, Los Angeles, or somewhere in between. It helps us bring more of these untold stories to light. Now let's get back to March 1940, because what Balsden realized in that moment would rewrite everything crews thought they knew about survival. He landed the Wellington at Mildenhall just before dawn, climbed out, stood beneath the starboard wing and stared at damage that should have killed him. Ground crew gathered silently, counting holes, running hands over exposed framework. 63 penetrations. The fabric hung in tatters. But every geodetic member remained intact, bent perhaps, scored by shrapnel, yet holding. In that moment, staring at his skeletal bomber in the pale English morning, Balsden understood something the Air Ministry had known, but crews had doubted. They weren't flying a weakness. They were flying a revelation. The story began 9 years earlier, in a design office that smelled of blueprints and slide rule calculations. Barnes Wallis wasn't sketching dreams. He was solving a problem that had killed too many airmen in the previous war. Conventional aircraft construction relied on main spars, a few critical load-bearing members running through wings and fuselage. Hit one, sever it, and the structure folded. Wallis had already revolutionized airship design with the R-100, using geodetic framework that distributed loads across entire structures, rather than concentrating stress on singular points. Now he turned that principle toward bombers. The mathematics were elegant. Instead of 4 main spars carrying most structural load, create thousands of load paths. Each curved duralumin strip, about 2 inches wide, followed geodesic lines across the aircraft's form, the shortest paths on curved surfaces. Where strips intersected in opposite spirals, they were joined. Every intersection distributed stress outward to neighboring strips. Damage 1 strip and loads flowed through surrounding lattice. Damage 10 strips and the same redistribution occurred. The structure degraded gracefully rather than snapping catastrophically, but the fabric covering baffled everyone. Why wrap this mathematical marvel in Irish linen when metal skin was clearly superior? Wallis's answer was ruthlessly practical. The geodetic frame already provided all structural strength needed. Metal skin would be dead weight. Fabric doped tight over framework was waterproof, aerodynamic, and weighed a fraction of aluminum sheet. More critically, fabric wouldn't crack or tear catastrophically like metal. A shell fragment punching through aluminum created stress risers at tear edges, potentially peeling entire panels away. Fabric just made a hole. The airframe didn't care. The Air Ministry took convincing. Test pilots at Brooklands initially treated the prototype like it might dissolve mid-flight. But wind tunnel tests and structural analysis were undeniable. On paper, at least, the Wellington could absorb battle damage that would destroy conventionally built bombers while maintaining structural integrity sufficient to return home. Theory was one thing. Reality over the Ruhr would be quite another. When new crews arrived at RAF Marham in early 1939, they couldn't believe what they were seeing. These fabric-covered contraptions looked like they belonged at air shows rather than frontline squadrons. Flight Sergeant James Ward later recalled his first impression. "I thought someone was having us on. My mate nudged me and said, 'They've given us bleeding kites.'" The Vickers Wellington sat on hard standing, fuselage visibly covered in doped linen over what appeared to be basketwork framing. Touch it with your knuckles and it drummed like canvas tent. The nickname arrived immediately, borrowed from J. Wellington Wimpy, the hamburger-loving character from Popeye cartoons. But there wasn't affection in it yet. just disbelief tinged with dark humor. Meanwhile, the Luftwaffe had all-metal Heinkel Wunderlebens and Junkers 88s. Solid, modern, reassuring. The Wellington seemed a relic from the 1920s, which in many ways it was. Training instructors at operational conversion units heard the same questions repeatedly. How was fabric supposed to stop flak fragments? What happened when incendiaries hit it? One instructor at number 15 OTU finally snapped, "Listen here. You lot think metal's some magic shield. Metal tears, metal cracks. This." He slapped the Wellington's flank. "This bends, flexes, and keeps flying." The crews nodded politely and remained unconvinced. The comparison seemed brutal. The Armstrong-Whitworth-Whitley was all metal. So was the Handley-Page-Hampton. These looked like proper military aircraft, smooth, stressed skin construction, riveted panels, the weight and solidity that inspired confidence. The Wimpy looked like someone had stretched fabric over a greenhouse frame and hoped for the best. Walk around a Wellington on the flight line, and you could press your palm against fuselage and feel the geodetic basketwork beneath fabric. Ground crew could patch battle damage with fabric and dope carried in tins, like mending a torn shirt. This was supposed to carry 4,000 pounds of bombs to Berlin. By September 1939, Wellingtons equipped 8 frontline squadrons. The brass spoke confidently about geodetic principles and structural redundancy. The crews getting operational assignments spoke about hoping they'd survive long enough to transfer to something made of proper materials. They'd climb aboard their Wimpy, settle into positions surrounded by fabric and basketwork, and wonder exactly what brilliant mind had decided this was adequate protection against the most modern air defenses in the world. The first operational sorties weren't dramatic deep penetrations crews had feared. Throughout winter 1939 into early 1940, Bomber Command stuck largely to nickel operations, leaflet raids where Wellingtons droned over Germany dropping propaganda rather than bombs. Crews called it bump raiding and treated it as the longest paper route in history. But it gave them something valuable: experience with German defenses while everyone was still learning rules of this new war. Squadron leader Henry Pleasance of Number 9. Squadron remembered the pre-flight atmosphere in February 1940. Chaps would tap the fuselage before climbing in like they were checking if it was solid. One pilot said, "Right then, let's see if this kite holds together when Jerry starts shooting." Nobody laughed. We were all thinking it. Then came real operations. March 19, 1940, Ballston's raid on seaplane bases. Several aircraft came back with damage. Neat holes punched through fuselage fabric. Some geodetic members dinged but not severed. A few control surface tears. Ground crew patched them with fabric and dope overnight. The aircraft flew again the next evening. It wasn't heroic yet, just quietly unexpected. One hole didn't multiply into catastrophic failure the way everyone had assumed it would. April brought heavier raids. Stavanger Sola Airfield on the 17th. Wellingtons tangled with German fighters for the first time in force. The pattern repeated through May and into June. Wellingtons were coming back with damage that should have been catastrophic but somehow wasn't. A number 38 squadron aircraft returned from Mönchengladbach with over 60 flak holes. Ground crew counted them individually. The pilot reported only slight sluggishness in controls. The fabric looked like something from a fairground shooting gallery, but the geodetic frame beneath was doing exactly what Wallis had promised, redistributing load around damaged areas. Crews started comparing notes. The metal Whitleys and Hamptons were coming back too, but when they took serious hits, results were different. Metal skin would tear along rivet lines, whole panels would peel away. Structural members would crack completely when struck. A Wellington took a hit and you got a hole. A Whitley took a hit and you got structural compromise. The difference wasn't academic when you were nursing a damaged aircraft over the North Sea in darkness. By June 1940, the nickname Wimpy had begun its subtle transformation. It was still used universally, but now something almost affectionate crept into it. The aircraft looked absurd, certainly. Sounded ridiculous, absolutely. But it was bringing them home when it had no business doing so. Wireless operators would pat fabric beside their positions like you'd pat a reliable dog. One rear gunner chalked "bendable but unbreakable" on his turret's interior. Nobody was openly admitting they'd been wrong yet, But the doubt was cracking. December 16, 1940 became the night that changed minds. Mannheim was the target, an industrial city deep enough into Germany to test crews properly, defended heavily enough to matter. 134 bombers went out that night. The Luftwaffe was waiting. So was the Flak. What came back settled arguments that had been brewing since first operations began. Wellington, L-78 Waitin of number 149. Squadron landed at Mildenhall just before dawn. The duty officer walked out to meet it and stopped dead. The rear fuselage looked like someone had taken a giant cheese grater to it. Flak had torn away fabric in sheets, exposing geodetic framework across a section nearly 10 feet long. You could stand beside it and count individual lattice members, see right through the structure to the other side. The tail gunner, Sergeant Ronald Clark, climbed out white-faced but alive. He'd watched tracer fire ripping through fabric inches from his position, felt the aircraft shudder as shells detonated nearby, and somehow they'd flown 4 hours back to England with half the rear fuselage effectively gone. But L-78 wasn't unique that morning. Wellington R-1236 came back with its port wing so shredded that ground crew could poke their heads through holes large enough to climb through. The geodetic members were visible, some bent, some scored by shrapnel, but none completely severed. The wing still generated lift. The aircraft still responded to ailerons. Flight Lieutenant James Penhill had nursed it home, assuming any moment the wing would simply fold. It never did. Number 99. Squadron's Wellington T-2553 provided the most dramatic evidence. A night fighter had raked it nose to tail with cannon fire. The fabric covering hung in tatters. Entire sections of geodetic framework were exposed to slipstream. 3 separate compartments were open to sky. The navigator, Pilot Officer Dennis Field, later wrote, "I could see stars through the roof, through the walls, through the bloody floor. We were flying inside a skeleton, but we were flying." Ground crew counted 127 holes, 127 points where structure had been penetrated, and the aircraft simply carried on. The comparison with other types from that same night told the darker story. 2 Whitleys went down over target. Post-operation analysis suggested both suffered catastrophic structural failure after taking flak hits. A Hampton managed to reach the channel before its damaged rear fuselage section tore away completely. The crew bailed out over water. 3 survived. These were all metal aircraft, supposedly superior in construction, supposedly more robust. They'd taken similar hits to the Wellingtons and they disintegrated. Photographs taken next morning at Mildenhall and other Wellington stations circulated quickly. Intelligence officers documented damage meticulously, trying to understand what they were seeing. Engineering officers examined exposed geodetic framework, measuring deflections and studying how loads had redistributed around damaged areas. What Barnes Wallis had promised theoretically was demonstrably true practically. Remove 10% of geodetic structure, and the remaining 90% simply shared load more widely. Crew rooms buzzed with new conversations. Pilots who'd flown Hamptons before converting to Wellingtons talked about the difference in damage tolerance. Wireless operators compared notes about continuing to transmit from stations that were technically no longer enclosed. The mockery had died completely. When someone said "Wimpy now," they meant it the way you'd reference a trusted mate who looked ridiculous but always came through. December 16th hadn't just brought aircraft home. It had brought proof. Understanding why required looking at how metal bombers were built. The Handley Page Hampton used stressed skin construction. The aluminum alloy skin wasn't just covering, it was structure. Rivet the skin panels to internal framework of stringers and formers, and the skin itself carries aerodynamic loads bending and flexing as aircraft maneuvers. It's efficient, lightweight, and it has a fatal flaw. Damage the skin, and you've damaged primary structure. A shell fragment penetrating aluminum skin creates a hole, certainly, but more dangerously it creates stress risers at tear edges. Aluminum wants to crack when stressed, and those ragged edges are where cracks start. Under flight loads, particularly during evasive maneuvers or turbulence, those cracks propagate along rivet lines. One hole becomes a tear. A tear becomes panel separation. In May 1941, operational research examined 17 Hamptons lost over Germany. 9 showed evidence of catastrophic structural failure following relatively minor flak damage. The skin had unzipped. The geodetic structure degraded gracefully. It didn't snap. The redundancy was mathematical. A conventional bomber might have 4 main wing spars, 20 stringers, and 200 rivet lines holding critical structure together. Sever 1 main spar, and you'd lost 25% of primary load paths. Sever 2 and the wing was finished. The Wellington's geodetic lattice had thousands of load paths. Each individual member carried a tiny fraction of total load. Destroy 50 members, truly catastrophic damage, and you'd lost perhaps 5% of load carrying capacity. The structure simply redistributed forces through remaining members. North Africa brought different challenges in the same impossible survivals. By early 1941, Wellingtons were operating from primitive airstrips in Egypt, hitting Italian positions in Libya, and dodging increasingly competent German fighters that had arrived to support Rommel's Africa Corps. The harsh environment should have exposed every weakness in the fabric and lattice design. Desert sand infiltrated everything. Temperature swings from scorching days to freezing nights stressed materials. And the distances meant damaged aircraft had hundreds of miles of hostile territory to cross before reaching safety. No. 70 Squadron's Wellington Z-8835 became legendary in June 1941. Hit by flak over Benghazi Harbor, it took a direct strike that blew away a 6-foot section of the port wing's leading edge. Not fabric damage. Actual structural members were severed. The wing's forward geodetic lattice was gone, replaced by empty air. Physics said the wing should have folded backward under aerodynamic loads. The pilot, Flight Lieutenant Kenneth Barker, felt the aircraft lurch violently left, countered with opposite aileron, and found it still responded. The remaining geodetic structure had redistributed the wing's loads, the rear lattice members taking on forces they weren't originally designed for, but handling them nonetheless. Barker flew that aircraft 240 miles back to base. The damaged wing generated less lift, so he kept the aircraft in constant slight bank to compensate. Fuel consumption increased because asymmetric drag required constant rudder pressure, but it flew. Ground crew at Fuka examined the damage and couldn't understand what they were seeing. Remove that much structure from a conventional wing, and you'd have instant catastrophic failure. The geodetic principle was doing something that defied intuitive understanding, spreading loads through paths that shouldn't have existed. By late 1941, Wellington crews in North Africa had stopped questioning their aircraft's resilience. They'd watched it proven too many times. One pilot summed it up. "Jerry can shoot us full of holes and we'll wave at him on the way home." The written record preserves their voices. Logbooks, letters home, post-war memoirs where men who'd flown Wellingtons explained what changed. Flight Sergeant Thomas Murray of No. 15 Squadron wrote in his diary after a raid on Cologne in May 1942, "Called it Wimpy for months like everyone else, thought it was a joke. Now I'd take this fabric kite over any metal job they offered. 3 times Jerry shot us up proper, and 3 times she's brought us home. The lads kiss the fuselage after landing now. Not joking about that." Pilot Officer Robert Woolworth's letters to his wife traced the evolution clearly. October 1941. "Still flying the Wimpy. Looks like a bloody circus tent with engines." March 1942. "Wellington took a beating last night. Fabric torn to shreds over the rear section. Flew perfectly fine. Starting to understand why the old hands trust it." July 1942. "Wouldn't swap this aircraft for anything. It's kept me alive when sleeker machines haven't managed the same for others." The operational record speaks in numbers that retrospectively justified every crew's faith. Between September 4, 1939 and October 8, 1945, Wellingtons flew 47,490 bombing operations. The actual sortie count exceeded 100,000 individual flights into combat. No other British bomber came close to that operational tempo sustained across 6 years of war. Survival statistics tell the deeper story. Overall, Wellington losses ran at approximately 3.4% per sortie during the height of Bomber Command's strategic offensive in 1942 and 1943. The Sterling during the same period lost 5.2% per sortie. The Hampton, before its retirement from European operations in late 1942, averaged 4.8%. The difference seems marginal until you calculate what it meant for crews. A Wellington crew had roughly a 67% chance of completing a 30-operation tour. A Sterling crew had a 51% chance. That 16% difference represented hundreds of lives. Post-war analysis vindicated Barnes Wallis completely. The Royal Aircraft Establishment at Farnborough conducted exhaustive structural studies between 1946 and 1948, examining surviving Wellingtons alongside crashed examples recovered from across Europe. Their conclusions were unambiguous. Geodetic construction provided superior battle damage tolerance compared to any contemporary stressed skin design. An RAE report from March 1947 stated flatly that catastrophic structural failure from combat damage occurred at rates approximately 60% lower in geodetic airframes than conventional monocoque construction. The German Luftwaffe's technical intelligence had reached the same conclusion earlier. Captured German documents from Rechlin Test Center recovered in 1945 showed Luftwaffe engineers had examined shot-down Wellingtons and were baffled by the structural resilience. One report from October 1942 noted, "The English basket frame construction absorbs damage in ways our calculations suggest should be impossible. Recommend structural analysis to determine if principles can be adopted." They never did adopt it. Too complex to manufacture, too different from established doctrine. Which raises the obvious question. If geodetic construction was demonstrably superior for battle damage survival, why did it disappear? Why aren't modern aircraft built this way? The answer lies in brutal arithmetic of aerospace engineering. The Wellington's geodetic frame required approximately 11,000 individual fabricated metal pieces for the fuselage alone, each precisely formed, each requiring skilled labor to assemble. A Lancaster's fuselage used roughly 2,000 components. Manufacturing time for a Wellington fuselage, 800 man-hours. Lancaster fuselage, 350 man-hours. In wartime, when you needed thousands of aircraft quickly, that difference was decisive. The Wellington's battle damage tolerance was magnificent. Its production efficiency was terrible. As war progressed and bomber losses mounted, the Air Ministry needed volume over survivability. 4-engine heavies like the Lancaster could be built faster, carried heavier loads, and though they were more fragile when hit, you could replace them quicker. Grim calculus, but inescapable. The geodetic principle also faced aerodynamic limitations. The fabric covering, though adequate for Wellingtons operating at 15,000 feet and 230 miles per hour, wouldn't work for aircraft pushing 300 miles per hour or operating above 25,000 feet. Fabric couldn't handle the higher dynamic pressures. When the Air Ministry finally retired the Wellington from frontline bombing duties in 1943, it wasn't because the aircraft had become ineffective. It was because 4-engine heavies could carry 3 times the bomb load over longer distances. The Wellington hadn't failed. It had simply been superseded by operational requirements it was never designed to meet. Those final missions in 1945 were flown by crews who'd never known the pre-war skepticism. They'd trained on Wellingtons, trusted them implicitly, and felt no need to question why fabric covering worked. For them, the Wimpy was simply what a reliable bomber looked like. The final Wellington, a Mark X trainer, flew its last sortie in March 1953. By then, the crews who'd flown them operationally were mostly civilians again, telling stories about the fabric bomber that looked ridiculous and flew impossibly well. The aircraft that began as Wimpy the joke had ended as Wimpy the lifesaver. Modern aircraft use stressed skin monocoque construction because it's efficient, manufacturable, and adequate for peacetime operations, where battle damage isn't expected. But the Wellington's legacy persisted in subtler ways. Modern damage-tolerant design, the principle that aircraft structures should degrade gracefully rather than fail catastrophically, traces directly back to lessons learned from geodetic construction. Multiple load paths, structural redundancy, fail-safe design philosophy. These are now standard in aerospace engineering. The Wellington proved that survivability matters, that bringing crews home justifies structural complexity, They realized they weren't flying a weakness wrapped in fabric. They were flying mathematics wrapped in Irish linen, and mathematics, as it turned out, was stronger than any metal skin could ever be.